Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be discussing the Archimedean property of reals, and before that let us briefly recall what we have done so far. So far in the first module, the basic agenda was to define what is meant by real numbers and show that they exist and they are unique, although we did not show that they are unique. So let us recall, the field of real numbers is defined as any ordered field which has the least upper bound property, meaning whenever a subset of it has an upper bound, it also has a least upper bound. Okay, and we have these notations that suppose we have a subset A of R, suppose it is bounded above, then this denotes the least upper bound of that set. And if it is not bounded above, then we just write this to mean infinity, this symbol. We just declare that equal to this thing. And that's just a shorthand to say that this does not have an upper bound. Similarly, we have notions of lower bound and greatest lower bounds. And this is the notation for that. So basically, this is what we have done so far. And now for the problems. Two very interesting and important problems to get comfortable with the notions of least upper bound and greatest lower bound, etc. Okay, now let us get to the material of this lecture. So what we'll be discussing is the Archimedean property, and for that we first need a very simple looking lemma, but it is not exactly trivial. So the lemma is that the infimum of this set is 0. So this thing is a subset of real numbers which is bounded below by 0. So it has a greatest lower bound, and the claim is that the greatest lower bound of that set is actually 0. And that's intuitively obvious, but it is not exactly trivial to show. I mean, there is an idea which is not obvious, I would say. Okay, so let S be this set which is of course a subset of R, and it is clear that S is bounded below by 0. Okay, and therefore it has a greatest lower bound, and let A be equal to the greatest lower bound of S, and we want to show that A is equal to 0. But then note that by the fact that A is the greatest lower bound, it is at least a lower bound, and therefore A is at most any element in S. So we can write this for all natural numbers, which implies that A is smaller than this for all natural numbers. Okay, so please note this step, which gives us that 2A is at most 1 upon n for all natural numbers, which implies 2A is a lower bound. But since A is the greatest lower bound, we have 2A is at most A. Okay, and also note that A is non-negative. So here we can just immediately say that A is non-negative because 0 is a lower bound. So the greatest lower bound should be at least as much as 0. It should be greater than or equal to 0. So A is a non-negative number, and as soon as you have this for a non-negative number, this implies that A is 0. So that's it. That's the proof. So very simple looking fact and also very important. Okay. And now we can write down what is the Archimedean property of reals. So here is the theorem. This is the Archimedean property. So it says that let x and y be two real numbers where x is positive. So then there is a natural number such that nx is greater than y. So let's prove this. So if y is non-positive, then the theorem clearly holds. That's simply because this is positive. So if this is positive and this is less than equal to 0, then of course this holds. So we may assume y is positive, and now since the infimum of this set, as we just showed, is 0, there is some natural number, let me call that n0, such that one upon n0 is smaller than x upon y. So why is that? That's because if this was not the case, then for each n we would have this, and then the infimum of this guy would be at least as much as that guy, but that guy is positive. So the observation is that this is positive, which is not much of an observation anyway. And since the infimum is 0, this should become smaller than every positive thing ultimately. So we have this for some natural number. And that's it. So that gives us that y is less than n0 x, and this is what we wanted to prove. So this is called the Archimedean property of the real numbers. You can define it for any ordered field, but we don't need to do that. We have proved Archimedean property for real numbers. Okay, and a corollary of it is something that I would like to point out, that if y in R is arbitrary, then there is a natural number. There is a natural number n such that n is greater than y. So why is that? Just substitute x equals 1 in the above. So you get n greater than y. So that's it. So basically it is saying that the set of natural numbers is not bounded above. Again, a trivial looking fact, but one has to prove it. Okay, so lastly, let me give just a definition, nothing to do with Archimedean property. It's a definition that I have to give at some point, so I choose it to give it now. And this, I'm sure, is familiar from high school. So basically, what I'm trying to define is the intervals in real line. So first we define the closed interval, a comma b. So a and b are some real numbers where a is less than or equal to b. So let me write that. A is less than or equal to b. And the closed interval is all those real numbers which are between a and b, including a and b. And we should always have a picture in mind. So this is my real line. This is, let's say, a, and this is b. Then the closed interval is all these points, including the endpoints. This is your closed interval. And similarly, this is the open interval, a comma b, where you do not include the endpoints. And let me also draw a picture. So this is A, this is B, and here we just take the points which are kind of inside. We do not include the boundary points. And similarly, all of these definitions, you can pause the video and read all of them. All of these are called intervals, and these are precisely the intervals in the real line. So just a definition. So that's it. That's all that I wanted to discuss in this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.